All right, in 2.9, we are going to look at applied optimization, which is based off from you were finding max and minimum in the last section, and now we'll see what those are used for. For example, in business, you might want to maximize profit and revenue, but minimize cost. And there's other uses for it too. So let's take a look at what some of those are. Number one is the max-min story problem technique from your textbook. So basically, I like to revise that a little bit and just say, you got to figure out what you need to minimize or maximize, and you got to make sure you have a function for that. And once you do, then you just set it equal to, or take the derivative, set it equal to 0, and solve, and that's going to give you your min or max. Sometimes it's not so easy to find the function, but let's look at one that a function is already given for you. So c of x is 7,150 plus 250x plus 0.8 x squared, and the demand function p of x equals 750. So we want to find the production level that will maximize profit. Well, we weren't given a profit function per se, but let's think about what profit is. So the function p of x is going to be revenue, or r of x, minus c of x. Well, we have r of x, or no, we have c of x rather, but r of x we do not have a revenue. But let's think about this. Revenue is equal to the price times quantity sold, or x times p of x, little p of x for price. And little p of x was actually given. So r of x is just 750x. So we can plug those in here. R of x is 750x. And then subtract the cost function. So it's going to be minus 7,150 minus 250x and minus 0.8x squared. Then we can take the derivative of that. R prime of x is equal to 750. Let's see, minus 250 minus 1.6x. In other words, 500 minus 1.6x. So we're going to set that equal to 0. And solve it, and you should get that x is equal to 100 and, oh, actually, no, let me plug that in real quick. 500 divided by 1.6 is 312.5. So that is going to be the production level, or the amount that we're going to produce to maximize profit. So in earlier sections, we would actually make sure that that was a min or max by using either the first derivative test or second derivative test. But for applications, you don't really need to do that. It doesn't hurt to do that to make sure that you did find the max or min. But typically, whatever your critical point is going to be the max or min. If you have multiple critical points, then sometimes you can figure out that one of them isn't really going to work, and we'll see that in a minute. All right, a baseball team plays in a stadium that holds 60,000 spectators. With the ticket price at $8, the average attendance has been 27,000. When the price dropped to $5, the average attendance rose to 30,000. Assume that the attendance is linearly related to ticket price. What ticket price would maximize revenue? All right, so we know that, well, first of all, we want to maximize revenue. And again, revenue, or R of X, is equal to price times quantity sold. I'm just going to say quantity. And the attendance, or the attendance would be the same as quantity sold, right? So that is a linear function. It's really linear related to price. So let's see if we can figure that out. We're given 2 points. We're given 8 27,000 and 5 30,000. So if we find the slope, that's 30,000 minus 27,000 all over 5 minus 8. Simplified, that's negative 1,000. I'm going to use the first point and plug it into the equation y equals mx plus b. So 27,000 equals negative 1,000 times 8 plus b. Solving for b, we get 35,000. So our attendance, or our quantity, is y equals negative 1,000 x plus 35,000. So to get revenue, we just need to multiply that by the price, which is x. So x times that is equal to negative 1,000 x squared plus 35,000x. All right, from here, we would find the derivative of the revenue function, which is negative 2,000x plus 35,000. Set that equal to 0 and solve for x, which gives us the critical point, but that value will also be what maximizes the revenue. So a simple linear equation to solve, and when you do, you should come up with 17.5. So in other words, $17.50 is what we want to charge the baseball fans in order to maximize revenue. Alright, so they're going to get a little more difficult here. This one is a box with a square base and an open top. Must have the volume of 275,684 centimeters cubed. We wish to find the dimensions of the box that will minimize the amount of material used. Because if this is, say, a cardboard box, we'd want to use the least amount of cardboard to ship our product so that we save costs. So this problem might seem a little overwhelming, and that might be true with a lot of the problems, and you might think I have no idea how to start this. And that's okay, because you've never seen this type of problem before, but as you do see more and more of these problems, the technique will start to seem more obvious. So, for example, in the last 2 problems we did, we just had to find what the function was. And once we got there, it was just a matter of finding the critical point. So we're going to do the same thing here. We are trying to minimize volume, or sorry, area. So let's write that down. We want to minimize area or material. So we need a function, and I'm going to call it m of x is equal to the material used. Well, we don't know what the dimensions of this box are, so let's start giving it some. It's a square base, so the two bottom dimensions are the same, x and x, to give it a square base. And then the height is going to be h, it's some other number, because it's not a cube, or at least we don't know if it's a cube, so h and x are not necessarily the same. So each, for the material used then, the square base will give us x squared, 'cause that's how we get, so I can draw in here. This red area here, x times x, is going to be the material at the bottom of the box. And then if we want any one of these sides, like the one I'm going to shade in green, the amount of material for that would be h times x, or x times h. And there's 4 sides, so it'd be 4xh. Well, this is all well and good, except if I take the derivative of it, I don't know what to do with that h. So let's see if we have any other information in our problem that we haven't used. And I see that we are given information about the volume. Well, volume is equal to length times width times height, and in our scenario it would be x squared times h. Well, then that x squared times h is equal to 275,684. Aha! From there I can solve for h, and I get that h is equal to 275,684 divided by x squared. So I can replace that h now with something in terms of x, which is the 275,684 over x squared. Cleaning that up a bit, I'm going to multiply the 4 by the 275,684. I'm going to get 1,102,736, and we can divide out 1x with 1x. We're left with an x in the bottom, but I'm going to bring it up to the numerator and make it x to the negative 1, because my next step is to take the derivative. So the derivative is 2x minus the 1,102,736, x to the negative 2. Unfortunately, we would want to, why am I running out of room? Minimize that. We want to, well, not unfortunately, but since the next step is to set it equal to 0, I'm going to put that x to the negative 2 back in the denominator, because for solving it's better to have them be positive numbers. So it's going to be minus 1,102,736 over x squared equals 0. Multiply both sides by x squared and we get 2x cubed minus 1,102,736 equals 0. And that's pretty easy to solve for x, and you should get that x is 82. All right. Put that teeny tiny there. And then finally, that gives us the 2 dimensions of the bottom of the box, but if we want h, remember that h is equal to 275,684 over x squared, so over 82 squared, and you get that that's 41. So we get the dimensions of 82 by 82 by 41 centimeters squared, or cubed rather. That's what's going to minimize the box. All right, let's see if we can go to the next problem. That should work. All right, a piece of cardboard measuring 11 inches by 10 inches is formed into an open top box by cutting squares with side length X from each corner and folding up the sides. So I have a little diagram here of what's going on. We start with a rectangular piece of cardboard and we start cutting out little squares on the edge, and then you can fold up the sides and make a box. And we want to maximize the volume here, so we need to write down the volume. So remember that volume is going to be length times width times height. Well, the height of our box, well, let's just look at what this box looks like here. It's going to, oh, that's terrible. Let's start over. Going to look something like this. And the height of the box is going to depend on how much we cut out from each corner, so I'm going to call that X. Everything that we cut out on the corners, it's X by X because it's squares. So the height is X, no problem. Now the length and the width, if we're cutting out X on each side and the original length, or width in this case, was 10, then it's going to be 10 minus 2x after we take away the x on each side. And likewise, it'll be 11 minus 2x for the length. So that gives us our volume function. And if we multiply that out, we get 110x minus 42x squared plus 4x cubed. Take the derivative of it, and we get 110 minus 84x plus 12x squared. So we'll set that equal to 0, and since it is a quadratic function, you can use your quadratic formula program from your calculator. And you should get that x is equal to either 1.74 or 5.26. Now with 5.26, if I took that away on this side here, 5.26 on this way and this way, I end up with negative material, and that doesn't make sense. So if we cut away about 1.7 inches on each corner, then we're going to maximize the volume of our box. Alright, in E, we have a rectangle inscribed with its base on the x-axis and its upper corners on the parabola, y equals 12 minus x squared. What are the dimensions of such a rectangle with the greatest possible area? So we should draw a picture so we know what's going on. And 12 is about right here, and it's a parabola going down, so it looks like this. So we're trying to inscribe a rectangle between the x-axis and it can't go further than the graph. So we don't know if it's going to look like this, kind of squarish, or if it's going to be more narrow, like this. We don't know which one is going to give the better area. But we are trying to maximize area, so that's the function that we want to look at. And area is just length times width. Or in this case, we'll call it width times height, because we're talking about the height of that graph. Well, the width of either one of these rectangles, if I look at the green one or the red one, the width of it is just going to be x. It's whatever x value we land on here. And it's going to be x on, you know, the same amount on both sides. So we get 2x to give us our width. Now it's technically negative x on the other side as your point, but because we're talking about length here, we want absolute value. So it's going to be x plus x gives us 2x for that width. Now the height of either of any of these rectangles is just going to be y. So 2x times y. But we don't want to have multiple variables in our function, so we're going to replace y with the given function, which is 12 minus x squared. Multiply that out and we get 24x minus 2x cubed. We can take the derivative of that, equals 24 minus 6x squared. Set it equal to 0, and we will get that x is equal to 2. So 2 is probably closer to the red one, 2 and negative 2. So the total width is 4, and the height would be 12 minus 2 squared would be 8. So it'd be 4 times 8 gives us an area of 32. So that's the maximum area that we can get for that particular one. And our last problem in this section is about a farmer. She finds that if she plants 75 trees per acre, each tree will yield 25 bushels of fruit. She estimates that for each additional tree planted per acre, the yield of each tree will decrease 3 bushels. How many trees should she plant per acre to maximize her profit? All right, well, we're trying to maximize I said profit, I meant harvest. We're trying to maximize her harvest, so we need a function. We'll call it h of x for harvest. And what is the harvest going to be? It's going to be the number of trees times the number of bushels. That'll give us how much, what are these, apples or something? So that'll give us how many apples that she's actually going to get, which means she can sell those apples and make money. Okay. And we're given a little information. We know that for 75 trees, I'll call it T, we get 25 bushels for B. Now if I do 76 trees and I only get 22 bushels, according to, let me do it in red, this line right here, because each additional tree, the yield of the tree will decrease by 3 bushels. And one more if we do 77 trees, and we're down to only 19 bushels. So based on that, we're going to try to figure out what this h of x is. I want to make sure I keep that up. So h of x is going to be the number of trees. Well, it's going to be 75 plus however many more we plant. We'll just call it x. So if we plant one more at 76 and we only have 22 bushels. So the number of bushels, we start off with 25, but every time we plant an additional tree, we lose 3 bushels. So that's going to be minus 3x. So even though x is going to be the number of trees, we can use that based on this information here to get the number of bushels that are going to be left. And you can check to make sure it works. Like I said, if x is equal to 1, so h of 1, and we get 76 times 25 minus 3, which is 22, and that's what we expect. If we do 2 more trees, then we have 77 trees, and now we're only down to 19 bushels. So it works with what we know up here. So let's just multiply it out, FOIL it, and we're going to get 1875 plus 25x minus 225x minus 3x squared. And we'll clean that all up. So that h of x is equal to 1875 minus 200x minus 3x squared. Taking the derivative of it, we get negative 200 minus 6x. Set that equal to 0. This is finding your critical point. And solving, we get that x is equal to negative 33.3. So what does that mean? That means that this farmer should actually plant about 33 less trees in order to maximize her harvest. So the question is, how many trees should she plant per acre? Well, instead of 75, she's going to do 75 minus 33.3, which is equal to 41.7, which is about 42. So 42 trees is going to maximize her harvest. And we can go back and look at this, at these numbers. So if we do 75 and 25, then the yield for 75 and 25 is 1875. 76 times 22 is 1672, so it goes down. And 77 times 19, it goes down even more. So the more trees she plants, the worse it gets. However, if we only do 42 trees, then that's going to give us extra bushels. So it's going to be 25 minus 3 times 33.3, because that's what our x is, times negative 33.3. So that is 124.9, and we multiply that by what are we down to? 41.7 or 42 approximately, and then we get a grand total of 5,245.8 bushels. This isn't part of the problem, but it's just to show you that, that it works. That if you actually play with the numbers, if you put the numbers back in, what we found maximizes the harvest actually does maximize it.